EFD 22. Okay, those who can leave the meeting, they can rejoin. So એક જણો એક ટેકનિકલ એરરના લીધે લીવ થઈ ગયો છે, that can he can rejoin the meeting after 2 minutes. Okay, fine. So in the previous lecture we have talked about this if the differential equation, second order linear differential equation of this type, where this x0 is an ordinary point, that means that p of x and q of x are analytic function in the neighborhood of x0, then this differential equation has a unique solution. Furthermore, the solution is also exist where the power series of p of x and q of x are exist. And based on that, we have also solved certain examples. And in the previous lecture also I have discussed regarding the same, that what will happen if this p of x and q of x are not analytic at the point x0. That means that point, it's called the singular point. So I already discussed the definition of the singular point. So what is the definition of a singular point? The singular points are those points where the function p of x and q of x are not analytic. If p of x and q of x are not analytic, at x0, then x0 it's called the singular point. In that situation, we need to calculate, or we need to find out what will be the general solution, or what will be the series solution for this differential equation. So to understand that, we have to learn about very important topic. It's called the regular singular point. So what is the regular singular point? It says that this x minus x0 p of x. See, first of all, you should have this x0 is the singular point, and then we can talk about the regular singular point. Okay. So if x0 is a singular point and this x minus x0 p of x and x minus x0 square q of x are analytic at x0, then we can say that this x0 is a regular singular point. So you understand what is the definition? The regular singular points are those points where this x minus x0 p of x into x minus x0 square q of x are analytic. Okay. For example, in particular, if I take this example, x cube x minus 1 y double dash minus 2x x minus 1 y dash plus 3x y equal to 0. So this equation I can rewrite as y double dash minus 2x x minus 1 upon x cube x minus 1 y dash plus 3x upon x cube into x minus 1 y equal to 0. Then if you compare this equation with y double dash plus p of x y dash plus q of x y equal to 0. So comparing with this, we get p of x will be this, that is p of x is, you just observe that is x cube x minus 1 is cancel out and 1x is cancel out. So it is minus 2x square, and q of x is 3 upon x square into x minus 1. One should note that this p of x and q of x, actually p of x is not defined at x is equal to 0. So hence it is not analytic at that point. This q of x is also not analytic at x is equal to 0 and 1. So I can say that x is equal to 0 and 1 are the regular singular point. What I can say, x is equal to 0 and 1 are not regular singular points. Why they are singular points? Because this p of x is not analytic at x is equal to 0. Q of x is not analytic at x is equal to 0 and 1. So that's why x is equal to 0 and 1 are the singular point. Now if it is a singular point, we are able to find out what is the regular singular point. So from this, we need to calculate what is the regular singular point. For that, the things is you have to check whether x minus x0 into p of x, whether this function is analytic or not. So that is x, first I am starting with taking your x0 equal to 0. That means I am first checking for 0 and then we will check for 1. So it is x into p of x we have. That will be minus x into 2 upon x square is there. X get cancelled out, so it is minus 2 by x. This is not analytic at x is equal to 0 because it is not defined at that point. So we can say that this function or this p of x, this differential equation does not have, or I can say that x is equal to 0 is not a regular singular point because this function are not analytic at that point. Therefore, what I can say, x is equal to 0 is not a regular singular point. Okay. Now next, we have to check for x0 equal to 1. So according to that, it is x minus x0 into p of x, which is x minus 1 into p of x. And p of x is already known that it is minus 2 upon x square. So it is minus x minus 1 into 2 upon x square is analytic at x is equal to 1. That we can say by just checking, by seeing it. This is analytic at x is equal to 1 because it is the polynomial function, polynomial upon polynomial function. So it is analytic at x is equal to 1. The next we have to check whether x minus x0 square q of x is analytic or not. That is x minus 1 square q of x. And the q is this which we have 3 upon. So it is x minus 1 square into 3 upon x square into x minus 1. X minus 1 get cancelled out. So we will have 3 into x minus 1 upon square. Again, it is a rational function. So it is analytic at the point x is equal to 1. Since this x minus x0 p of x is analytic at the point x is equal to 1, and the second function x minus x0 q of x is also analytic at the point x is equal to 1. So we can say that this x is equal to 1 is an regular singular point. Okay. So that we need to write down here. X is equal to 1 is the regular singular point for this function. Let me give you one more example to do it yourself. So do for this second example, x square into x square minus 1 y double dash minus x into 1 minus x y dash plus 2y equal to 0. The question is find the regular singular point for this differential equation. Okay, so I'm giving you to try this example by your own. So take up a notebook and pen and solve this. I'm giving you 2 minutes to do this. So first task is to calculate the singular points. Singular points, for that you have to check whether, or at those points where the p of x and q of x are not analytic. So first of all, you have to calculate what is the value of p of x as well as q of x. So if you can compare this equation with y double dash plus p of x, y dash plus q of x, y equal to 0. Comparing with this, p of x will be minus x into 1 minus x upon x square into x square minus 1 by dividing x square into x square minus 1 both sides, and q of x will gives you 2 over x square into x square minus 1. Now the p of x that you can have here will be x is cancelled out and this x square minus 1 this x square minus 1 can be written as x minus 1 into x plus 1. So this why this 1 minus x will cancel out and this minus goes away. So that's it is now converted into 1 over x into x plus 1. Q of x that you can write down as 2 upon square into x minus 1 x plus 1. So one can observe that this p of x is not analytic at x is equal to 0 as well as minus 1, and q of x is not analytic at x is equal to 0, 1 and minus 1 due to they are not defined at that point. Okay, so what we can say, therefore the singular point for this differential equation are 3, 0, 1 and minus 1. They are the singular points. Since we have a singular point, we need to calculate what are the regular singular points. So for that I need to check what is happening with x is equal to 0, for x is equal to 1 and for x is equal to minus 1. So we'll do for x is equal to 0. So for x is equal to 0, you have to check what is x minus x 0 into p of x. That is x minus x0 into p of x, which is x into p of x, and p of x is this value. So x into p of x will be 1 upon x plus 1 is analytic at x is equal to 0. that we have. The second one is x minus x0 square q of x. The q of x is this, so that's why it is x square q of x is there, and x square will get cancelled with this x square here. So this will gives you x square minus 1 is also analytic at x is equal to 0. So what you can say, x is equal to 0 is the regular singular point. Okay. Now similarly you can check for x is equal to 1, what will happen, and x is equal to minus 1, what will happen. So x is equal to 1, once you have, it is x minus 1 into p of x. What is this function? You will get yes, guys. So it is 2 into x minus 1 upon x square into x plus 1. Please mute your mic, those who have unmute. Unless you want to speak, don't unmute your mic. Who is singing? Please unmute your mic. Okay, so we can observe that this function, that is x minus 1 into p of x, is analytic at x is equal to 1, and x minus 1 square q of x will be 2 into x minus 1 upon x square into x plus 1, which is also analytic at x is equal to 1. So therefore x is equal to 1 is the regular singular point. Now similarly for x is equal to minus 1, can you do that yourself? Can I give you as a homework? Yes or no?
Yes, sir.
Yep.
Okay, so what is the answer? Whether it is the regular singular point or irregular singular point. The point which is not regular, it's called irregular singular point. What is x plus 1 p of x? It is 1 upon x, which is analytic. Yes, what do you get?
So it is not a regular singular point.
It is not a regular singular point. Okay, you can just check that. So now next example, that is x square y double s plus 2x 2 minus x y equal to 0. So try to solve for what is the regular singular point for this. This I can write down y double s plus 2 minus x upon x square y equal to. I think so this is also easy example. Here p of x is 0 and q of x is this 2 minus x upon x square. That I'm also giving you as a homework that you can do it by yourself now. I think so you are able to do that.
Yes, sir.
Okay. Now let us give you one more example. Y double dash plus sin x y equal to 0. This is the fourth example that I have taken. The question is to calculate what is the regular singular point for this. So it is obvious by comparing the standard equation y double dash plus p of x y dash plus q of x y equal to 0. P of x will gives you 0 and q of x will be sin x. This p of x is already an constant function. So p of x is analytic. P of x is also analytic everywhere. So we can say that this x is equal to 0 is an ordinary point. Okay? In particular. बराबर है? Since what I can write is since p of x and q of x are analytic everywhere, because sine function is also analytic everywhere because it's differentiable everywhere. So it is analytic everywhere. So therefore, all points are ordinary point. All the points are ordinary points. I'm just slightly modifying this example. Instead of y double dash, I just write down x into y double dash plus sin x y equal to 0. Now again comparing with this differential equation and rewriting this equation as y double dash plus sin x upon x y equal to 0. We have p of x is a constant function which is 0 and q of x is a sin x upon x. Here we have to check whether this differential equation or what is the nature of the point x is equal to 0. That is our objective. Our objective is what? What will be the nature of the differential equation at the point x is equal to 0. That means whether this x is equal to 0 is an ordinary point, is a regular singular point, or it is a singular point. Okay, so that is we need to check. So here there is no problem with this p of x. Let us see whether this q of x is equal to sin x upon x is an analytic function or not. So anybody have answer for that? What you can say regarding this?
Sir, x is equal to 0 is a singular point.
Anyone else?
Sir, moreover, it is a regular singular point.
Okay. So why you have said it is a singular point?
Sir, because when we put x is equal to 0, then our q of x is becoming undefined. Sir, because there is no limit here. If we put limit x tends to 0, then it would be 1.
Okay. So now there is also, I have said that analytic functions are those functions for that the power series exist. I said that is also a definition is equivalent thing for those functions where the power series exist. So those functions are called the analytic function as well as the power series are exist or well defined or well behaved function. So here what is q of x? Q of x is sin x upon x. that I can write as a series of sin x. We know it is x minus x cubed by 3 factorial plus x raised to 5 upon 5 factorial minus x raised to 7 upon 7 factorial up to so on. And if you multiply this 1 upon x inside, then this can be written as 1 minus x square by 3 factorial, x raised to 4 by 5 factorial, x minus x raised to 6 by 7 factorial, and so on. So I can say that this q of x can be expressed as a power series. Can we say that?
Yes, sir.
So that means this q of x is an analytic function at the point x is equal to 0. So hence what we can say, q of x, there is no problem with the q of x. So what we can say, x is equal to 0 is an
Ordinary point.
ordinary point. Very good. It's not a singular point, it is an ordinary point for this differential equation. Fine. Let us give you another example by slightly modifying the previous example. So that I'm writing as x square y double dash plus sin x y equal to 0. So what is the p of x here? Again it is 0. Q of x is sin x upon x square. Now for this you have to check whether this q of x is analytic or it can be expressed as its power series. What you can say now? So you just observe that q of x you can write down as 1 upon x square into sin x, that is x minus x cubed by 3 factorial plus x raised to 5 by 5 factorial minus x raised to 7 by 7 factorial, and so on. Now if I x square multiply inside, this will have 1 upon x minus x by 3 factorial plus x raised to 3 by 5 factorial minus x raised to 5 by 7 factorial, and so on. Since the powers or this expansion of this q of x contains the negative power of x, that is 1 upon x, which is x raised to minus 1. So therefore I can say that q of x is not analytic at x is equal to 0. Okay, and therefore x is equal to 0 is the singular point. Since this is a singular point, you have to check whether it is a regular singular point or not. So for that you have to check what is the x into p of x, that is x minus x0 into p of x and x minus x0 into q of x. So that is x minus x0 p of x will be 0 due to p of x is 0, and x minus x0 square q of x will be x square q of x, which is x square into sin x upon x square, which is also sin x. So I can say that both these functions are analytic because sin x is analytic. So I can say R analytic at x is equal to 0. So therefore x is equal to 0 is the regular singular point for this ODE or for given ODE. Okay. Let me give you one more example. So write down x cube y double dash plus sin x y equal to 0. So try to do this example. So try to solve this. What is the nature at the point x is equal to 0? I am giving you as a homework this example. I hope so you can able to do this example by your own. So I think so now I have given you enough idea about the regular singular point and how to calculate the regular singular point. Has everyone understood what you mean by regular singular point and ordinary point? Yes or no? Yes, I want a response from you guys. Okay. So to solve now the differential equation which has the regular singular point, we have a method called the Frobenius method. Okay. And this Frobenius method gives you idea how to solve the second order linear differential equation. The second order linear differential equation is of this type. And we are assuming x is equal to x0 is the or x is equal to x0 equal to 0 is the regular singular point. Point for this differential equation. Suppose 0 is not a regular singular point. Then what we can do, we just substitute x minus x0 equal to t into this differential equation and convert the new differential equation in terms of y and t. So solution for this differential equation which is converted into y and t, which is also a solution for the same differential equation. So without loss of generality, we can assume that if the 0 is not a regular singular point, then you can convert your differential equation to the another differential equation for which you have a regular singular point. So that adjustment is needed if it is 0 is not a regular singular point. So by an average, we assume that x is equal to 0 is the regular singular point of the differential equation. And the method says that if x is equal to 0 is the regular singular point, then the quasi power series solution, and this is also known as Frobenius series. So what is that Frobenius series that I am writing here? Frobenius series is a solution is equal to x power m summation n running from 0 to infinity an x raised to n, where m is subset or belongs to R. This is known as quasi power series solution of a differential equation which has x is equal to 0 is a regular singular point, and which is also known as Frobenius series. Just changes in the power series. This is the power series an x raised to n. This is the power series, but with that we have multiplied x power m. So this is actually a series of this type, summation n running from 0 to infinity an x raised to n plus m, where n is some positive, or sorry, some real number. So this is, if you expand this one, then this will be x0 x raised to m plus a1 x raised to m plus 1 plus a2 x raised to m plus 2 up to so on. This is the series you have. Now if I differentiate this differential equation, or sorry, this series, then what do we have? So y dash, we will have summation n running from 0 to infinity an n plus m x raised to m plus n minus 1. See here, it will not start with 1 because this always has the term with the x power m. So if you can, this expanded form, that is m a0 x raised to m minus 1 plus m plus 1 a1 x raised to m plus a2 into m plus 2 x power m plus 1 and so on. This is the series you will have. If you do the second derivative, then again the series start with n equal to 0 to infinity n plus m minus 1 x power n plus m minus 2, and then if we expand this one m into m plus m minus 1 a0 x power m minus 2 plus m into m plus 1 a1 x power m minus 1 plus a2 m plus 1 into m plus 2 a2 is already I've written x raised to m and so on. So in that manner you will have the first derivative and the second derivative. Okay, what we have assumed that this x is equal to 0 is the regular singular point. What does it mean? X is equal to 0 is the regular singular point. That means we have assumed that x is equal to, or x0 equal to 0 is the regular singular point of the given ODE. Therefore, x p of x and x square q of x are analytic at x is equal to 0, that we can have. Okay, so if these are the analytic function, it has the power series, that is x p of x has a power series, that is summation n running from 0 to infinity pn x raised to n, that we have assumed, which is p0 plus p1x plus p2x square up to so on. And x square q of x also have the power series summation n running from 0 to infinity qn x power n, which is q0 plus q1x plus q2 x square and so on. So therefore, what is the p of x we can write? The p of x we can write as p0 plus p1x plus p2x square up to so on upon x. That x I can divide both sides and we have this. So hence q of x also we can write down in the same manner as this. Q of x is what is q of x? So what is q of x? Is q0 plus q1x plus q2x square up to so on upon x square. Now putting this value of p of x and q of x into the given differential equation, the given differential equation is this: y double dash plus p of x y dash plus q of x y equal to 0. So if I substitute this value into this, then this is y double dash into p0 plus p1x plus p2x square to so on upon x y dash plus q0 plus q1x plus q2x square up to so on upon x square y equal to 0. Again, we have the value of y double dash and y dash. We can substitute that value here and we compare the coefficient both sides. Okay, so let me write down what is y double dash. We have calculated n running from 0 to infinity m plus n minus 1 an x raised to m plus n minus 2 plus this whole quantity, that is p0 plus p1x plus p2x square up to so on upon x square y dash plus q0 plus q1x plus q2x square up to so on upon x square. So this is x upon x square. Here we have to write down y dash. What is y dash? N running from 0 to infinity m plus n into an x raised to m plus n minus 1, and this is summation n running from 0 to infinity m an into x raised to m plus n equal to 0. So I have substituted the value of y double dash, y dash and y as we have calculated previously, which we have did it here above. So we have calculated that value here. Okay, so that I have substituted into that differential equation. then what will be the lowest degree term into that? That means what is the lowest degree term is actually x power m minus 2. So in this series solution, or in this series, the last we have obtained it, what will be the lowest degree term into this series? So when I put n equal to 0, into that, this computer is running very slow. So in this, you just substitute n equal to 0. What will be the first term into the first series? What will be the first term you will have? When I substitute n equal to 0. Another summer say here what we get, here what we get. N equal to 0 if I substitute. See, if I substitute n equal to 0 into this series, n is 0, that is m. This will gives you m minus 1, a0, x power m minus 2. That is the first n equal to 0 માટે આ term આવશે. What about here? This is p0 upon x. So if n equal to 0, this term is m minus 1, x power m minus 1. So it is m a0 into x power m minus 1. And this x is multiplied to that 1 upon x. So it is m minus 2, it will convert, and the term you will have p0 into m. So the second term you will have p0 into m into a0 plus here if I substitute n equal to 0, this is a0 into x raised to m, but this x square, that is 1 upon x square, will multiply, then it will become x0, so a0 into x raised to m minus 2. So this q0 is also multiplied, so q0 by x square will multiply. So the finally when I substitute n equal to 0, this is the term you will have. So the lowest degree term into this series will be q0 into a0, and on the other side it is 0. So I am comparing actually a constant term both sides. Oh, sorry, not constant term. It is I am actually comparing the power of x minus 2 both sides, which is the lowest degree term, that is equal to 0. Have you understood this step, or I can repeat again?
Can you repeat again?
Okay, so if you understood, we can move forward. Then what I will do is I just take out this a0, which is common in each and every term here, common out. So what we'll get? We will get m into m minus 1 plus p into p0 plus q0 into a0 equal to 0. And we assume this a0 is not equal to 0. Hence, you will have this quantity will be 0. And this is known as identical equation or a formula. Identical equation or a formula. And this is actually a quadratic equation in terms of m. Why it is a quadratic equation in terms of m? Because it is m square minus m. You will have plus m p0 plus q0. So this is of the form m square minus or plus p0 minus 1m plus q0 equal to 0. So if you compare with x square plus ax square plus bx plus c equal to 0, then this equation will have two roots. Okay, so this equation, this identical equation has the two roots. Let's say that two roots are m1 and m2. See, what I am doing here, I am explaining what is the Frobenius method. Okay, and then later on we will solve using this method. So example of such problem. So here right now I am explaining what is the Frobenius method. So this identical equation has the two roots. The first root is m1, another root is m2. Okay, let us assume these are the roots. And if this m1 is the root, then the solution of the differential equation is this: y1 equal to x raised to m1 by putting the value of m into the original solution, that is x power m summation n running from 0 to infinity a n x raised to m. So this will be the solution of the given differential equation. And the another solution will be y2 will be x power m2 summation n running from 0 to infinity a n x raised to n, provided this y1 and y2 are linearly independent. If they are not linearly independent, we cannot write down the solution is of the form c1 y1 plus c2 y2, because the solution is always come under the linear combination of linearly independent variables. But here this y1 and y2 should be linearly independent, then and only then we can write down this is as a general solution. Otherwise we need to have, if they are not in linearly independent solutions, then you have to deal the differential equation with the different manner. Okay, so you need to find out another solution. That also we will discuss later on. But right now, this is the Frobenius method. So what is the Frobenius method? Is for when you have a differential equation which has this regular singular point at x is equal to 0. And then if it is not 0, then you can transform your differential equation into 0, and then you can do it in this manner. So let us solve some examples related to it, and let us discuss what is the solution or how to calculate the solution for such equation. So the equation is 2x square y double dash plus x into 2x plus 1 y dash minus y equal to 0. The question is to solve this differential equation. So first of all, I need to check whether the given differential equation has a regular point or regular singular point or ordinary point. If the ordinary point is there, x is equal to 0, then you have to do it the method which we already did in the previous lecture. Okay, that is by assuming your solution as a power series summation a n x raised to n, and then you can solve that one. That is if this x is equal to 0 is the ordinary point. If it is a singular point, Then you have to check for regular singular point, and then you can apply this Frobenius method. That is the things you can do it. So here y double dash is x 2x plus 1 upon 2x square y dash minus 1 upon 2x square y equal to 0. So comparing with y double dash plus p of x y dash plus q of x y equal to 0, we have p of x is, since this x is cancelled out, it is 2x plus 1 upon 2x, and q of x is minus 1 upon 2x square. So what we can observe, this is a rational function, this is also a rational function. Rational functions are those functions which are of the form p of x upon q of x, where px is the polynomial, qx is also polynomial. So we can observe that this p of x is not analytic at the point x is equal to 0, q of x is also not analytic at the point x is equal to 0, because that functions are not defined at that point. So therefore, we can say that x is equal to 0 is not analytic. Sorry, x is equal to 0 is not an ordinary point. Since this is not an ordinary point, we can try to check whether this x into p of x is analytic or not. So that is, we can just see that it is 2x plus 1 upon 2, and x square into q of x, which is minus 1 by 2, because x square will get cancelled out, and both of them are analytic at x is equal to 0. So therefore, what we can say? Therefore, we can say that this x is equal to 0 is the regular singular point. Since this is a regular singular point, we can assume the solution is y equal to summation n running from 0 to infinity a n x raised to n plus m. This is the solution we can assume. Now, what will be the y dash? Okay, y dash is the derivative of this, that is summation n running from 0 to infinity m plus n a n x raised to m plus n minus 1. Y double dash, that is summation n running from 0 to infinity m plus n minus 1 a n x raised to n plus n minus 2 by taking the derivative of x raised to m plus n. First derivative is this, second derivative will be this one. Substituting this value of y dash and y double dash into the given differential equation. Let us write down what is the given differential equation. Again here, so it was given that y double dash x square y double dash plus x into 2x plus 1 y dash minus y equal to 0. This was the given differential equation. Now we have to substitute this value of y double dash. So we have 2x square summation n running from 0 to infinity m plus n minus 1 a n x raised to m plus n minus 2 plus this I can write down by multiplying two brackets, that is 2x square into y dash. Y dash is this, so I may write down summation n running from 0 to infinity m plus n an x raised to m plus n minus 1. Then this x is multiplied to this 1 into y dash. So that's why it is plus x into summation n running from 0 to infinity m plus n an x raised to m plus n minus 1 minus y, that is summation n running from 0 to infinity an x raised to m plus n equal to 0. Let us simplify this. Okay, simplify this. Then this is summation n running from 0 to infinity m plus n minus 1 an x raised to, this x square is multiplied to this, so it is m plus n, and this 2 is also multiplied inside, so it is m plus n plus summation n running from 0 to infinity. 2x square will multiply inside, so 2 into m plus n an x power m plus n plus 1, because this is m plus n minus 1 plus 2, so it is this value you will have. Then you will have next term m plus n into an x raised to m plus n. So summation n running from 0 to infinity m plus n an x raised to m plus n. Then minus summation n running from 0 to infinity an x raised to m plus n equal to 0. Now, what will be the lowest degree term into this expression of x? The lowest power 30%. What will be the lowest power of x? So that I can observe that when I put n equal to 0 here. If I put n equal to 0 here, the lowest is x power m. Here it is x power m plus 1. Here it is x power m. Here is also x power m. So what I am doing is comparing coefficient of lowest power of x, that is x power m. Actually it is x power m to 0. So we can compare that lowest power to 0. So what is the lowest power into the first summation? So that you can observe n equal to 0, if I substitute, then it is 2m. So here it is m plus 0. This is m minus 1. So into m minus 1. A0. X power n is there. Here in the second term, that will be plus 2m A0. No, that is does not have the x power m term. So this term I have written wrongly. So you should not write this is as the second term. So in the third one, that is here, you will have x power m term. So it is m A0 plus here you will have A0 equal to 0. What is this equation? It's called identical equation that we already says. for identical formula, and we have to calculate what are the roots of this identical formula. So what do you get? A0 is non-zero, that we are assuming. Okay, so this equation we can rewrite as 2m square minus 2m plus m plus 1 into A0 equal to 0 by multiplying 2m inside. So this will give you 2m square minus m plus 1 equal to 0, as A0 is not equal to 0, that we have assumed. Now this equation will have two roots, that is 2m square minus 2m plus m this is of negative sign because here we have a negative. So that the last term which is having the negative sign instead of plus, so this is a negative, so therefore this will be negative, and this is also negative, so that's why it is negative of minus 1 equal to 0. So therefore it is 2m is common out, so it is 2m into 2m minus 1 plus 1 is common out from this 2, that is m minus 1. So therefore it is 2m plus 1 into m minus 1 equal to 0, that will give you m equal to 1 and minus 1 by 2. So there are two roots of this identical equation. First one is 1, another one is minus 1 by 2. See, it says that this Fibonacci's, this series says that, so here m1 is 1 and m2 is minus 1 by 2. It says that is m1 minus m2 is not an integer, then the solution y1 and y2 are alike, and there is no problem to write down the solution at all. If this m1 minus m2 is not an integer, sorry, it is an integer, then you have a strictly different method to deal with. Till then, if it is not integer, it is fine. So I am just writing for what is the solution for m equal to 1. So for m equal to 1, the coefficient of x power m plus 1 into the above equation star we get. Let us calculate that also. Why we have calculated m equal to 1, that is we need to write down the solution now, or I can write down the recurrence relation. In this equation, when I substitute n equal to 1, we'll have the m plus 1 term. Here when I substitute n equal to 0, we'll have m plus 1. Understood? So either you can write down into the recurrence relation, or you can do it in this manner which I am doing. How to write down the recurrence relation, that also we will discuss. But for now, we just write down what will be the m plus 1 term here. So this is 2 into m plus m. I am now substituting n equal to 1. 2 into m plus 1 here, that is into m a1 x power m plus 1, that is a coefficient for the first term. Here you have to substitute n equal to 0, that is 2m a0 Here you have to substitute n equal to 1. So that is m plus 1 into a0 x power m plus 1, that is the coefficient, and the last term will have minus a1. Here it is also a1. So finally you will have, this is the term which is the coefficient of x power m plus 1. Let us write down the same term here. That is 2 into m plus 1 into m a1 plus 2 into m a0 plus m plus 1 a0 go to 0. Now we have already m1 is 1, so we substitute that value here. So that's why this will gives you 2 plus 1, that is 4 is 1 plus 4 a0 plus this is a1. Huh? Let me check what I forgot. So it is m plus 1, a1 minus a1 is there. So that minus a1 I have forgot. M plus 1 a1 minus a1. So this is minus a1 equal to 0. And now I'm substituting m equal to 1. This will be 2 into 2. This is 2 into 1, that is a0. M plus 1, m is 1, so it is 2 a1 minus a1 equal to 0. If you simplify, you will have a1 equal to minus 2 by 5 a0. Same way, the coefficient of x power m plus 2 into that equation, what will we get? Oh God. Its screen is visible to you?
Yes, sir.
But here it is not visible. What is happening now? It's taking time. So in this, you have to write down what is the coefficient of x power m plus 2. Can somebody tell me what is the coefficient of x power m plus 2? In that, what you have to do is actually you have to substitute n equal to 2 into this. Here is also n equal to 2. Here you have to substitute n equal to 1, and here you have to substitute n equal to 2. So if you substitute n equal to 2 into this, then what we will get? 2 into m plus 2, m plus 1, then it is a2. Barabar? Here you have to substitute n equal to 1. That will gives you 2 into m plus 1 into a1. Here you will have m plus 1, m plus 2 into a2. So it is plus m plus 2 into a2. Then it is minus a1 for a2 equal to 0. So finally you will have, this is the expression when you compare the coefficient of x power m plus 2. So let me write down, that is here. That is 2 into m plus 2, m plus 1, a2 plus 2 into m plus 1, a1 plus m plus 2, a2 minus a2 equal to 0. Now put m equal to 1. What will have this quantity? This is 1 plus 2, that is 3, 1 plus 1, that is 2, that is 12 a2 plus 2 into 1 plus 1, that is 4 a1 plus 3 a2 minus a2 equal to 0. If further you simplify, this is a2 equal to, you will get 4 upon 5 into 7 a0, and so on. You will have further, if you compare the coefficient of x power m plus 2, you will have another expression in terms of a0. So ultimately our objective is to write down what is the solution. The solution is y equal to summation n running from 0 to infinity an x raised to m plus n is there. What is the value of m we have? We have calculated it is 1 for this. So it is an n plus 1. So if I expand this one, this is a0 x plus a1 x square plus a2 x cube and so on. The value of a0 is as it is. a1 we have calculated, it is minus 2 by 5 x square, that we have calculated earlier. a2 we have calculated just now, that is 4 upon 5 into 7 x cube and so on. So this is the first solution, that is called the y1. The y1 you will have this, and then we have to write down what is y2, that is for another quantity, which is for m equal to -2. What is you have to write down m equal to -2. So for m equal to -1/2, we already have calculated what is the coefficient of x power m minus m plus 1 and m plus 2 that we have calculated earlier. In that you have to substitute the value m equal to -2, where we have substituted m equal to 1. See, in this we have substituted m equal to 1, so we get this. So in this same formula, which is the coefficient of x raised to m plus 1, we have to substitute m equal to -2. Here is also we have to substitute m equal to -2, -1/2, not -2, -1/2. Here is also m equal to -1/2. Into both this formula, we have to substitute m equal to -1/2. So we will have the equation or relation which is in terms of a1 in terms of a0 and a2 in terms of a0. So let us do that. Substitute m equal to -1/2. This what we can get. Write down here. If I substitute m equal to -1/2 into this equation, can somebody simplify and tell me what is the a1 equal to? Should I open that one again?
Yes, sir.
See, so tell me what is a1 equal to? You have to substitute m equal to -1/2 here. So it is 2 into -1/2 plus 1, that is 2 into 1/2 into -1/2. So this will give you -1/2 a1, the first one. This gives you minus a0. This is minus plus 1/2 a1. That 1/2 is cancel out, and the last one is a1. So I think so a1 will be, last one is minus a1. So a1 will be minus a0 is the final quantity you will get. Will you get this one? Everyone? Secondly, you have to substitute here also and tell me what is the expression you will get. So I am just writing here. A1 we have got minus A0. A2 will get minus A1 upon A2, and that is exactly A0 upon 2. And if I substitute that is into the series summation n running from 0 to infinity an x raised to m plus n, which is summation n running from 0 to infinity an x raised to n minus 1/2. So when I have A0 into x raised to minus 1 by 2 plus a1 x raised to minus 1 minus 1 by 2, that is 1 by 2, plus a2 x raised to 2 minus 1 by 2, so it is 3 by 2, up to so on. So a0 is as it is minus 1 by 2 x raised to minus 1 by 2. The value of a1 we have got minus a0, so that is minus a0 x raised to 1 by 2. a2 we got, the value is a0 by 2, so it is plus a0 by 2 x raised to 3 by 2 and so on. And this is the another solution y2, and this y1 and y2 are linearly independent, and hence we can write down the solution which is of the form y equal to c1 y1 plus c2 y2, which is the general solution for given differential equation. Okay, so we'll stop here for today. See, this series solution example, I should suggest that you have to sit with the pen and paper and do it as you are doing in the class, in the regular class, because every time I needed the previous step to clarify the next step. So it is better you can solve as I am solving in my this digital board. You can solve that in your notebook, the same example, and in that way you can understand more, because this is not the subject that you can just see and you can learn. Here you have to do it, then only then you can able to learn this subject or this type of examples. Okay, so we will stop here for today. If you have any question you can ask.
સર ક્લાસ નોટની પીડીએફ
ઓલરેડી આપી દીધી છે
સર મોડલ પણ નથી.
એટલે 354 પેજની આખી હું જે ભણાવું છું એ ઓલરેડી શાંતિ પીસ ફોર મેથેમેટિક્સ તમે પ્રશાંત કુમાર પટેલ તમે ગૂગલ સાઇડમાં સર્ચ કરજો, ઇટ્સ ઓલરેડી અવેલેબલ there.
ઓકે સર, ઓકે.
મેં લિંક આપેલી જ
સર
છે.
એક યુટ્યુબ હેલો સર, યુટ્યુબ નો એક લેક્ચર ખાલી 8 જ મિનિટ નો બતાવે છે.
એમાં કંઈક પ્રોબ્લેમ છે. આજે મેં એક બીજો આજે રેકોર્ડિંગ કર્યા છે ને બધા મેં એક વિડીયો અપલોડ કર્યો છે આજે, બીજા હું 1-2 દિવસમાં અપલોડ કરી દઈશ.
ઓકે સર, થેન્ક યુ.
Okay, is there any other question? If not, then you can leave or you can leave the meeting.